We're going to take a moment and look at the kernel of a ring homomorphism in our first proposition. And we're going to show that the kernel of a ring homomorphism satisfies some properties that we're then going to abstract. So suppose that we have a ring homomorphism, phi from the ring R to the ring S. I'm just going to say is a ring hom. And as usual, let's let kernel be its kernel. Then for any R and R and XY in the kernel of phi, we have, well, first of all, we know already, I'm gonna put it as one of the things. We know this already. I'm just recording this first part that the 0 is in the kernel for a definition that's going to come shortly. Well, it's going to come in the next learning video. So that's our we always know that 0 is in the kernel. We know also that the sum of x and y is in the kernel if x and y are in the kernel. And we know that if I have my R and R, then Rx and XR are both in the kernel. So we have these three properties. Let's prove it. One, we already know. That is gold already. For two, we're going to suppose that x and y are in the kernel. Then what that means is when we plug them into phi, we get 0. Right? So we write out what it means to be in the kernel. Now phi of x plus y, well, phi preserves addition or is compatible with addition, so it breaks up in that way. And this is 0 plus 0, which is 0. I guess I subscripted my 0 on the R, so let's do it in the S as well. All right, so this tells us that x plus y is in the kernel because it's mapped to 0. So that's good, that's gold. And then 3, we have to show that the kernel absorbs multiplication by R. So suppose R is in R and X is in the kernel. Then, of course, phi of X is the 0 in S. Great. Now what? Well, let's compute phi of Rx, because that's the thing we need to show is 0. Kernel, sorry, the phi is a homomorphism, so it breaks up under multiplication. It's compatible with multiplication. And phi of X is 0, and anything times the additive identity is 0. So this tells us that Rx is in the kernel, that XR is in the kernel is similar, and I'll encourage you to do it. So I think that completes our proof here. Let's go back up to the statement. This first statement, 0 is in the kernel, that's the slogan. The next one is that the kernel is closed under addition. And I like to say the kernel sort of absorbs multiplication by R, but you can say whatever you like. It's not that the kernel is closed under multiplication. It certainly is, because everything in the kernel is in R, and it's closed under multiplication by R. But it's more than closed under multiplication. Just so as a cautionary note, this is more than closed under multiplication. Because not only is it closed by multiplication by elements of the kernel, it's closed under multiplication by every element in R. So I like to say instead that it's well, it kind of absorbs multiplication by r. If I take something outside the kernel and I multiply it with something inside the kernel, I get sucked into the kernel. But you could also say closed under multiplication by r. You can say whatever you like there. But I like to say absorbs. Okay, let me note one thing here as a quick consequence. So the proof has been done, but notice that for any xy in the kernel, we have, well, -1 is an element of R. It may not be in the kernel, but it's certainly an element of R. So -1 times y is in the kernel. So x plus this new element of the kernel, -y, is in the kernel. And this is what we, again, call subtraction. So the kernel actually, since it absorbs multiplication by r, the kernel is also closed under subtraction. And we could have seen that directly, but it follows from the other two properties.